Good morning, everybody, or good afternoon or good evening, depending on when you guys watch this. This is Mr. Arocena, and on today's lesson, we are going to be talking about the Arrhenius theory of acids and bases. This would have you would have seen this version of acids and bases back in grade 10 science, I think, because that's probably the first time you really studied acids and bases in any great detail. So this is going to be kind of a review of what acids and bases are based on what we learned in Science 10. All right, so the Arrhenius definitions of acids and bases are as follows. An acid is considered to be any substance that will create hydrogen ions. So this is a hydrogen ion. Hydrogen ion. So our Arrhenius acids will create hydrogen ions when they are dissolved in water. So if you put something in water and it releases hydrogen ions, it's considered an Arrhenius acid. Okay. By contrast, an Arrhenius base is any substance that releases a hydroxide ion. So the hydroxide ion is given by the hydroxide ion. Whoops. Hydroxide. Not to be confused with alcohol groups. An alcohol group is also an OH, but it's not an ion. Okay. So these are the definitions I think we learned in Science 10, where acids create hydrogen ions and bases create hydroxide ions. Okay. Now, a salt, this is a product that results when acids and bases meet with each other. If you remember from Science 10, neutralization reactions, you would get acid plus base will neutralize each other to create salt and water. Okay, so the salt is the result of the non-hydrogen, non-hydroxide ion that joins together to create the salt. Okay, so salts, and sort of another broader definition, these are ionic compounds. Ionic compounds. And they generally result from the neutralization of acids and bases. All right. Now there's another definition that I'll introduce today. This is not the final definition of acids and bases, just as a little foreshadowing. So another definition of acids and bases that you can sort of build off of the Arrhenius theory or Arrhenius definition. And this is, I guess, might have been taught to you as a quick trick or quick hack, I guess, tip to figure out whether a substance is an acid or a base. So any substance, any ionic compound, this is important, ionic, not organic. Organic acids are different. Any ionic compound that starts with an H. So example would be like hydrochloric acid or a hydrosulfuric acid or nitric acid. So these are all acids, and they're easily identified by starting out with an H. Okay, now these are ionic compounds. Okay, they're not organic compounds. Organic acids are different. Okay, we'll get to that later. And then sort of similarly, a base is anything that ends with an OH group. So anything that ends with a hydroxide. There are plenty of exceptions to this particular rule. So this is not a robust rule. This is kind of just like a quick and easy thing you can do to figure out if your substance is an acid or a base. Just look for the hydroxide group. So examples of this would be something like sodium hydroxide, that's a base, or potassium hydroxide, calcium hydroxide. These are all examples of bases because they all end in OH. But again, there are lots of exceptions to this. Quite a few bases don't actually end in OH, but they're still considered bases because of the other definition where they create hydroxide ions when they're put in water. Okay, so keep that in mind. Oops. And salts. Erase my... Salts will basically fall into the category that it doesn't start with an H and it does not end with an OH. So there's sort of three ways you can think of how to easily identify an acid, easily identify a base, and then again, easily identify a salt. Okay, and the key here is that this is for ionic compounds. Organic compounds are identified slightly differently. Okay, but we won't worry about that today. All right. So here's some examples of identifying which are acids and which are bases. Some of them I think I put in my examples on the previous slide. So if you pause the video here and take a few moments to identify, and then we'll see if you are correct. Pause the video, right? Pause the video. All right, let's see if you guys were correct. So the acids are the ones identified with the H's in front. So the HCl, the HNO3, H2CO3. So this is hydrochloric acid. So hydrochloric acid, nitric acid, and this is carbonic acid. The bases are identified by the ones ending in OH. Sodium hydroxide, potassium hydroxide. This one is zinc hydroxide. Okay. In later lessons, we'll give a much better definition of acids and bases and how you can better identify them. It's a little more complicated, but it's a much better definition of acids and bases. Okay. Now, going on to reminding ourselves of what a neutralization reaction is, because this will become important. A neutralization reaction is when acids and bases react and they will create salt and water. Now, one of the neat things about this particular reaction is that if you write it out, in almost all cases, the net ionic reaction ends up being the creation of water. Okay. So it's really neat. So if you recall from like the last unit, we were talking about net ionic reactions. When you write out the ions and everything that reacts, when you cancel everything out, all that is left is hydrogen ions reacting with hydroxide ions to create water. Okay, the salt will usually dissolve completely and is generally considered a spectator ion. Okay, so therefore the ions do not react because they are spectators. Spectator ions. And I'll go through an example of this. Let me just pull up my sketchbook. Okay, so an example of this would look like, let's take your typical base, sodium hydroxide. We'll react that with hydrogen chloride or hydrochloric acid. This will create, let me just move a little bit more room. Okay, this will create sodium chloride, there's my salt, and then water. I'm gonna write water like this because it's easier to work with, it's easier to balance when water is written this way. So if I break this into ions, I will get the following: Na plus OH minus. This will break down into hydrogen ions and chlorine ions. These are all aqueous because they are dissolved in water. So we'll write that down. Now here, this will create sodium chloride and HOH. This will be liquid. But if you check your table of solubility, sodium chloride is a soluble compound because it's got an alkali metal. Alkali compounds are generally very soluble. So this will, the sodium chloride will immediately dissolve back into sodium ions and chlorine ions, producing HOH like so. And then when I look at what appears on both sides, well, I have a sodium ion here, so I can cross that out. They don't actually react. The chlorine ion doesn't actually react either. So all we're left with is the following. The net ionic reaction is aqueous hydroxide ions plus aqueous hydrogen ions, all producing water. And most acid-base reactions will fall into this kind of net ionic reaction. There are a few exceptions. Generally speaking, if the salt ends up being if this one ends up being something like, I don't know, like a silver chloride or a lead chloride. something like that, something that makes a insoluble compound, then obviously you'll have an actual, like, your net ionic reaction will actually be bigger. But generally speaking, this salt is usually soluble. Not always though, not always, just usually. So be mindful of that, I guess, when you write out your net ionic reaction, if you're asked to do that, and then you just check, okay, check my table of solubilities. Does this combination here, does it create a low soluble compound or a soluble compound? Okay. All right. Now, when you're balancing neutralizations, if you noticed how I wrote my water as HOH, that's because it's generally easier to work with OH groups as opposed to individual oxygens and hydrogens. This way you can balance H's and then balance OH's on the other side. Okay? It works a lot easier that way. So here's an example. It's slightly more complicated than the other one because we're dealing with magnesium hydroxide. So if I write out my reaction, HCl plus MgOH2, I know this will create a salt. So the salt will be magnesium chloride. And then rather than writing H2O, I'm going to write HOH. Because this way you can balance out the OH groups. So I have an OH group in the magnesium hydroxide, and I've got an OH group in the water. So if I want to balance that out, I need two of them. So I'll put a 2 there. Okay, this will give me 2 H's. I need to balance out the H's over here. So I'll put 2 H's there. And I think that should balance everything out. That'll give me my 2 chlorines, which gives me my 2 chlorines over here. So lesson here is when you're balancing neutralizations, balance in terms of OHs and Hs. In almost all cases, that will be easier to do than balancing individual hydrogens and individual oxygens. All right. All right, here's another one. This is my ink. Oops, there we go. Ink. Now have you try this one on your own, so you can pause the video here, balance that reaction, and then we'll go over it. So pause the video, try it out, and when you're ready to see if you did it right, then you can restart the video. All right, so we had phosphoric acid, H3PO4. We are combining, I forgot what we were doing, calcium hydroxide, calcium hydroxide, like so. This will create a salt, calcium phosphate. Now make sure you are writing the correct formula. If you don't write the correct formula, this will make things a lot harder to balance. And then HOH. There we go. All right, so we're gonna balance, I don't know, I'll balance the calciums first. Yes, calciums were probably easiest to balance first. So I'll put 3 calciums to balance out the calciums. This unfortunately gives me 6 hydroxides, so I have to put 6 here to balance out the hydroxides. Now I've got 6 hydrogens, so I'm gonna go balance the hydrogens by putting a 2 here. That'll give me my 6 hydrogens, and then that'll give me 2 phosphates, which gives me 2 phosphates over here. So there we go. So this is your balanced chemical equation, or reaction equation for this. All right, now if you look at your table of solubility, I believe this particular salt is low soluble. So this is a low soluble salt. Soluble salt. So my net ionic equation would basically be this. This would be my net ionic equation. So this would be my net ionic equation for this particular neutralization, because this salt is low soluble. Unless I'm mistaken, but I'm pretty certain phosphate salts tend to be low soluble. All right, moving on. Okay, now Acids and bases have a lot of qualitative properties which you can use to help identify whether a substance you have is an acid or a base. So if you have an unknown substance and you're trying to figure out what is it an acid or is it a base, here are some qualitative properties that you can use to help identify them. First, acids and bases acids will react with bases to produce salt and water. So that's one easy way to tell. If you throw a base on it and it reacts and creates water, it's probably an acid. Are electrolytes. This is partly because acids create H plus ions in water. Right, so they release, so I shouldn't say create, they release hydrogen ions in water. So when they create hydrogen ions, that immediately creates an electrolytic solution because you've got ions in the solution. Okay. They will act on some metals to create hydrogen gas. Common metals that they will do this with will be like zinc, zinc, aluminum, no, not aluminum, zinc, calcium, sodium, magnesium. Acids will react on them to create hydrogen gas. Litmus paper will turn red for acids. Okay. Easy way to remember this is that red has a D in it, and so does acids. So acids turn red, or turn litmus red. And if you taste it, so taste it, not ingest it. If you taste the acid, most acids will taste sour. They all do. This is part of the reason sour candies generally have high acid content, because the acid is what gives sour candies their acidic or their sour taste. Okay. Now bases have a similar set of properties, although they're slightly different. Okay. So bases, they will, again, if you throw an acid onto a base, it'll create salt and water. So if an unknown substance, throw some acid onto it and see if it creates salt and water. If it does, it's a substance was most likely a base. Bases are also electrolytes because when a base reacts with water, it creates hydroxide ions. So hydroxide ions are created, and again, if you put ions in solution, you create electrolytes or an electrolytic solution. Bases tend to feel slippery. Part of that is because, if I remember correctly, bases will they have a good property of dissolving organic compounds. So they feel slippery because the base is breaking down the dead organic matter on your fingertips. And that's why it feels slippery, because basically it's turning your fingertips into like a weird goo of organic matter. Okay. Fun fact is that really, really strong bases can basically amplify that dissolving organic matter really, really well. Okay. All right. And then litmus paper turns blue in bases. This one's easier to remember because both the color and the substance start with the same letter. So if litmus turns blue, it's a base. Okay. And then bases tend to have a bitter taste. So this is why, like, if you've ever mixed up baking powder and baking soda, your baked good tends to taste very bitter because baking soda is a base and it will make everything taste bitter. Okay, but there you go. So some qualitative properties of bases. Okay. All right. Now, here are a couple of common acids and bases you might find lying around, either in your house, in your shop, or wherever you work. This is sulfuric acid. Sulfuric acid is the acid that is used in car batteries. We'll find out why we use acids in car batteries in the next unit after acids and bases when we talk about electrochemistry. But in short, car batteries contain highly concentrated sulfuric acid. Quite dangerous if it ever breaks or leaks out, so that's why you don't want to break car batteries. It's quite concentrated and quite dangerous. Okay, hydrochloric acid, this one your body creates all the time in your stomach, also causes heartburn because heartburn is basically your stomach acids creeping up through the esophagus. So quite literally, heartburn is your stomach eating yourself. Yeah. Also, why gut injuries tend to be quite dangerous, because if your stomach gets punctured, then the stomach acids will slowly eat the inside of your body. Yeah. The acid in your stomach is quite good at dissolving proteins, though, if I remember correctly. This one, oops, let me erase this. Let me erase that for a moment. Acetic acid, this is an organic acid, okay. And like I mentioned, organic acids look very different. So this is an organic acid. You notice the organic acid doesn't actually start with a hydrogen like the other two, and oddly enough, it actually ends in an OH. So, like I said, organic acids tend to be, they have much different structure than ionic acids. But anyways, this is acetic acid. This is an organic acid. Quite commonly, this is vinegar. The vinegar you get in the stores and what you use in cooking is actually quite dilute, so it's not very dangerous. But as you concentrate acetic acid, it can get on the same level of danger as some of these other acids up here. Like in our lab storeroom, we've got incredibly concentrated organic acetic acid, and it's quite dangerous to work with. So much so that the fumes themselves will actually burn your nostrils and cause quite a mess. Okay. Sodium hydroxide. This is most commonly found in drain cleaners. So if you ever had to clear a clogged drain, sodium hydroxide is probably what you're going to end up using. A more powerful variant of this is potassium hydroxide. So industrial drain cleaners will probably have potassium hydroxide as opposed to sodium hydroxide. Depending on what kind of brand you're using and the concentrations, both can be quite dangerous. So keep that in mind. Be careful with those if you ever use them to clear a drain. Oh, and don't pour it down your toilet. Pouring drain cleaner down toilets is a bad idea. Yeah. All right, ammonia. So this is ammonia. This is another cleaner. It's a great cleaning agent. Interestingly enough, if you notice with ammonia, there is no OH ion here, but it's still classified as a base. So this should give you guys kind of like some of you hopefully are thinking, it's like, well, why is it a base then? If there's no hydroxide ion, how can it create hydroxide ions? So you guys should be thinking about that. Okay. Anyway, so this is a cleaner, good for cleaning organic messes, not so good for cleaning inorganic messes. Okay. There you go. So those are some common acids and bases and the properties of acids and bases, kind of sort of in a nutshell review from what we learned in Science 10. Okay. All right, if you have your textbooks at home, this is the assignment questions you should be doing to sort of review what we've just done. And if you have any questions about it, you all know how to reach me. All right, enjoy the rest of your day.